Well, welcome everybody. My name is Barry Miller. I'm the Director of Outreach and Business Development for the Virginia Tech Helmet Lab. And what I thought I'd do is I'm going to give you guys a quick little virtual tour. I know it's fairly quick. Dr. Mark Begonia is going to be operating the camera for me. He's our Director of Testing for the Helmet Lab. So it should be about 15 minutes tour, unless you guys have some lengthy questions and discussions that we get into, but it'll give you a nice flavor of what we do. All right, welcome to the Helmet Lab. So the Virginia Tech Helmet Lab is a comprehensive injury biomechanics laboratory. We're best known for our helmet research. We test and rate helmets based on concussion risk. So that's probably where you see some of our STAR helmet ratings, www.vt.edu/helmet. It'll give you a bunch of ratings for football, hockey, cycling, soccer, flag football. So we test all those helmets and rate them. And we also get ready to launch snow sport helmets and equestrian helmets. We'll also do some sensors that are used in helmet and wearables for measuring head accelerations and things of that nature, kinematic data. So I'm standing in the hallway. We would love to have you guys here in person. But this is our entryway. And on the wall here we have a couple of helmet displays. The one on the left here is our football helmet display. This displays our original helmet ratings from 2011. And this is kind of the batch of helmets that we rated. And as you can see, this was 10 years ago. So it's quite a long time ago that we did these first ever ratings. You can see the different structures and materials, thicknesses, densities of all the helmets they tried to use to help improve performance. Unfortunately, by and large, with that first initial sample set back in 2011, the resulting scores, 0 stars being bad, 5 stars being very good, most of the helmets were 1 star, including our own football team. So the next year, we obviously put them in a 5-star helmet to reduce injury risk. But in a nutshell, what a helmet's designed to do, it's designed to attenuate all that energy and slow down head accelerations, both linear, so linear acceleration, as well as any rotational acceleration. And so, as you can see, a variety of materials and structures are designed to try to do that. Some are effective, some are not. It varies by company. This is kind of the latest, greatest helmet by Riddell. This actually uses a 3D printed inner helmet matrix of foam/rubber. This helmet's highly effective in doing what it does. And when I do a demo of the Pendulum Impactor, you guys will see that firsthand. So let me back up and I'm going to talk about how we've been measuring things. So somewhere back in about 2007, Dr. Duma and Dr. Rosen founded the Helmet Lab. What they started doing was putting these sensors, these little red dots inside the helmets. These are accelerometers. And so for every head impact this helmet receives, that data is recorded. Well, we start recording every practice, every game of our Virginia Tech football players. And when there's a concussion diagnosed on the field, that's when we pay particular attention to that data set. And so we pair it with on-field concussion data or diagnosis with what the helmet says. So now we have, after 10 years, we have over 2 million data points. And we have a really good idea of when certain acceleration values, linear and rotational, get to a certain level, then concussion risks, yes, start to increase, right? Somewhere around 100 Gs of linear acceleration and maybe 6,000 radians per second with rotational acceleration. But this is important. So we've been collecting this. We continue to collect data, and we're not the only institution that does this. So there's lots of data on there. In a helmeted situation, what kinds of head accelerations can you tolerate before concussions are likely to occur? We also done some wearable type information or kinematic studies. This is a mouthpiece with sensors in it. Our PhD student, Emily Kiefer, who's now actually Dr. Kiefer, studied our men's and women's rugby clubs, and they use mouthpieces. And so this technology it's getting better. Obviously, probably not as reliable and valid as a helmeted situation, but you're going to start to see these wearable type sensors used to give you a general information of, hey, that was a bad head impact. What was it? And Did I have a concussion? Or maybe I should get checked out even though I don't have a concussion. The mouth guard says I had 150 Gs of linear acceleration. That's bad. That's not good things. So you'll start to see these. Other side of the entryway here is our hockey helmet display. The first thing people in the lab or tourists notice is that these helmets don't nearly have as much padding as the football helmets. And as Mark zooms in here, obviously you can see that most of the helmet ratings for the hockey helmets are 1 star, 2 star, maybe even 0 star. They're not a very high performing helmet at this point in time. There's only a couple, maybe a handful of helmets that are 3, 4, or 5 star. So we're looking for some advancements. They haven't adopted the technology that are in the football helmets just yet, but it's coming. And so we have a couple new companies that are looking to enter that hockey market, which is primarily dominated by Canadian companies at this point in time. So we're looking for some advances in that aspect. So anyways, we'll move on. So as I mentioned, we do a few sports: football, hockey. We also do soccer, flag football, and we're getting ready to launch rugby. I don't know if I mentioned that before. So you guys might have seen some of these headbands and things that are worn for soccer. This goes on, right? You wear it on your headband, or full headgear like this one. Well, I'm not going to put that on, but so these types of full headgear, we call them soft headgear. And so it's not a hard surface like a football helmet or a hockey helmet or lacrosse or some of those other sports. So, there's a lot of bodily contact, so they don't want anybody to get scratched or cut. So this is called soft headgear. And with this particular test setup is what we call our head-to-head. So we have 2 head forms. One of the head forms is equipped with accelerometers and sensors inside, and then the other one is not. And so for soccer and flag football, rugby, usually the worst case scenario is when 2 hard surfaces collide, being your heads. That's usually the worst case. 2 soccer players go up to head the ball, they miss the ball, they hit each other, and that's when these concussions start to happen. Now, these head impacts are really fast, 5 to 10 milliseconds. Obviously, if one's padded, one's not, it actually makes that a little bit longer and flattens out the curve. So you don't get those peak acceleration values that we try to avoid. So this is our head-to-head. I'm going to show a demonstration. What we do is we measure the bare head versus the helmeted head to see how well this soft headgear reduces those acceleration values. We use a couple different speeds, a couple different locations, and that's how we run this test matrix. So we have a weight stack attached to this test rig. And so as I release the magnet, the weights fall and it accelerates this device or this test rig, so the helmet actually hits the other helmet. All right, you ready, Mark?
Second. Okay.
3, 2, 1. So that's how we do that. This test setup is also used for if we're doing baseball or softball or maybe shooting some other type of implements. We can put a big cage over this, rotate this head, and shoot point blank right at the face mask, catcher's gear, etc. To determine how well that type of helmet reduces head impact or head acceleration. So, all right, I think we'll move on. Any questions about that test setup at this point in time?
Yep.
No questions?
Not yet.
All right, this next test rig is what we call our Pendulum Impactor. So we have a big long pendulum arm, right? We have an impactor face, and then again we can set the helmet on a head form with a neck, and even a mass torso that resembles human torso. And so we can set this up and orient it any location, pretty much any angle that we'd like. And for football and hockey, we do 4 locations and 3 different energy levels. The nice thing about the pendulum impactor is if we take this up to the same angle every time, we should get a nice reliable velocity at impact. Other test devices uses air pressure, which isn't as consistent. And so we like to use the pendulum. Again, another thing that's really nice is once we get it on the helmet and set up in the right spot, it's nice and consistent with other people running the test because really the head form's in the right place. You just put the helmet on, strap up the chin strap, and away you go. All right, so we're going to run a sample here for you. And Mark's going to zoom in on the head of the helmet itself. Now I'm going to take this up to just about 90 degrees.
When you're right.
And so at 90 degrees, we call this our high energy impact. And if you did not have a helmet on, this impact would have somewhere around 300 or more G's of linear acceleration. That's the threshold where skull fractures and death occur. And that was kind of the impetus of creating helmets to be mandatory back in the late 50s, early 60s, somewhere back then. We went from leather to these pretty much virtually unchanged plastic helmets until really the last 10, 15 years. So there's different structures inside, but for the most part, it's a plastic carbonate shell. And so anyway, so this helmet will take that 300 G plus hit. It'll take it down to 120, maybe even under 100 for the best performing helmets, which may or may not even be a concussion. So it's a lot of energy that this helmet absorbs in a very short amount of time. So here we go. 3, 2, 1. So as you can see, that's a pretty big impact, and can't imagine what that would do to me if I didn't have a helmet on. So any questions? And we do hockey the same way, 4 locations, 3 different energy levels, and again, we can orient the helmet and head form in just about any position we want. One thing we do with these sport-specific STAR helmet testing protocols is we try to simulate as best we can what really happens on the field. And so, what locations are most common, what types of velocities are these players hitting their heads, and obviously thus the energy that is imparted during these head impacts. Some sports are easier than others, but we do a lot of video analysis, capture a lot of video, watch a lot of video, and then we kind of come up with these formulas to figure out what's appropriate. It's not easy to best replicate in a lab what happens on the field, but I think we do a really good job. And we're one of the few helmet labs that actually do sport-specific testing. As I mentioned earlier, so helmets have to pass a certification. I think I mentioned this anyways. So for every sport or type of use a helmet is made for, it has to pass certification by some company or some organization. For football helmets, it's the National Operating Committee for the Standards of Athletic Equipment, better known as NOCSE. For equestrian helmets in the United States, they use the American Society for Testing Materials. And these test setups, these pass-fail, as I mentioned, have to keep the helmet under a certain threshold, which is somewhere around 250, maybe 300 Gs, depending on the test and the certification and the type of helmet it is. But what's unique about these, or maybe not so unique, so this helmet just lifts up, it drops right down on the, and so it only measures linear acceleration. And as you guys have probably learned in some of your classes, that linear acceleration is one reason why you get a concussion, but it's also the rotational acceleration. As your head tries to maintain its position inside the skull, it's that stress and strain on the brain that causes concussions. Your brain doesn't have to hit the side of your skull. That'd probably be a really bad injury. So any of that stress and strain can cause concussions. So it's the same thing kind of with the equestrian helmets. They call this a two-wire drop tower, dropped onto an anvil. And oftentimes, these steel anvils are different shapes. And so this is like a curb or an angled anvil. And so the helmets, depending on what certification standard is, they have to pass certain thresholds for certain types of anvils that simulate maybe the sport. So this is a curve that we use kind of a flat surface for our helmet to helmet or a mushroom shape. So it's a little bit of variety, but we really fill in the gap between catastrophic injury and concussion risk. We rate helmets based on how well they're likely to reduce your chances of getting concussion wearing a given helmet model. And so we rate them against each other. So we fill a big void in that. The certifications are really important, but that's where we come in. We only test and rate helmets that are certified for the given sport. So we'll move on to the bike tower testing.
Quick question. What majors utilize the helmet lab?
Not too many graduate students might use the lab for their testing and designs, but for the most part, we employ undergraduates, a lot of mechanical engineers, maybe some industrial engineers, material science, a couple of health, nutrition, fitness, exercise that come in here and they want to get some work experience. We pay really well actually on campus. They run all the tests. There's thousands of tests we run, so it's very tedious and time consuming. And so we need a lot of help to do that. Usually it's the grad students, if they're working on some sort of project, may come in and utilize the lab. And then obviously we have PhD students in biomedical engineering that help us design, run these protocols. In fact, hockey, football, these were all assigned to grad students for the most part. That was their PhDs. Like I said, I mentioned Emily Kiefer, her PhD was with the mouth guard sensors in the rugby clubs. Megan Bland did the bike tower and the bike helmets. A guy named Eamon Kempa-Latano did the youth football study. And so oftentimes the grad students get assigned a project. And so that's kind of how they, every PhD has to have a project at some point in time. That's their dissertation. So there's probably a little bit more to it than just the helmet ratings, but that's a big piece of their projects.
Do you know of any other sport-related labs?
There's a lab called BioCore that's at UVA, and that one's sponsored by the NFL. And so they have their own lab, which is really similar to ours. They test a little bit different, higher energies. Obviously, they're evaluating NFL helmets with professional football players. Our helmet protocol is really designed for high school and college players. So, but if you looked at their ratings and you looked at our ratings, it almost identical as far as the helmet performance. They may be flip-flopped in a couple situations, but for the most part, they mirror each other. As far as other helmet labs, there's some certification labs that, again, run these basic tests, these standards that are created by these organizations. And so they'll take samples of given helmet from a company and say, yes, that helmet passed or it didn't pass. That's how they get the NOXY stamp or the ASTM stamp sticker, whatnot. So I think there's a lab at Stanford, helmet lab. Again, they might be injury biomechanics labs.
Yeah.
But again, and that's what we are, but we happen to specialize in concussion risk and helmet performance. So at least that's what we're best known for. And that's probably the bulk of our work for sure. So, all right, we'll move on to the bike tower. And Mark will probably give you a nice picture of all the helmets we have stacked. We're actually getting ready to expand the lab. We're going to blow out a wall over here on the other side of the bike tower to give us a little bit more space and make room for the equestrian and the snow sport helmet star ratings that we're getting ready to come out with in the near future. But lots of helmets. As you can see, boxes and boxes. We need lots of samples, lots of models to provide a nice, robust star rating system. So bike helmets are a little different than football and hockey helmets. Football and hockey, those helmets stay on the whole game. They don't come off. They get lots of hits. And so they're a multi-impact use helmet. So they're designed to last the whole season. They can take the punishment and the multiple impacts without degrading or reducing their performance level. Bike helmets, on the other hand, they're designed with this EPP foam, which kind of is like a hard, dense foam. And what that's designed to do is crush, crumble, and break on impact. Obviously, the energy for that given impact's got to be great enough for that to actually happen. And so we do see a lot of injuries at low energy levels where the helmet's not damaged, but you still get a concussion. So that's very different than some of the football technologies. But again, these are very lightweight. And again, single use. So once you crash on your bike and you have some sort of degradation or crumbling, breaking of the helmet, it's not going to perform as it was once designed to, so you should probably replace it. There's some technologies in here. I don't know if Mark will be able to get the yellow one. No? Okay, yeah, that one. So this helmet has this little yellow stickers called MIPS, Multi-Directional Impact Protection System. And basically what it does, it provides a little slip plane. Hopefully you guys can see that. See how my thumb can move, but the helmet stays stable? So that's what we want. We want the head to stay stable as the helmet moves, right? So it provides a slip plane between your helmet and your head. And so thus, if I was wearing the helmet and got into an accident, buying a little bit more time, absorbing a little bit of that rotational energy greatly reduces your chance of getting a concussion from that particular component in the head impact. So that's called a slip plane, called MIPS. There's a couple other, they call these rotational mitigation technologies. This one's called the Liat turbine system. So you got these little blue pucks, and they're designed to spin and rotate and absorb energy, and similar to the MIPS. So you'll start to see a lot of these in the helmets out there, especially the newer ones. So we're going to show you a bike tower impact test. So if you were to So if you were to wreck on your bike, so you move forward on your bike, and if you were to fall off your bike, so you have that horizontal component and the vertical component, so you typically fall at some sort of angle. Well, all the research and all the videos we've watched and the injury reports, we determined that it's roughly about 45 degrees. And as I mentioned with the pendulum, gravity is a great consistent source of energy. So what we did here, we invert and we drop vertically using gravity. But to simulate that 45-degree angle, we actually fall onto a 45-degree anvil. And we also put a little sandpaper on that anvil to simulate the road grit. That road grit becomes kind of important if you think about it. So here I have two smooth surfaces hitting each other, and they just glance off each other, right? But if one of these had sandpaper on it, what's going to happen? It's going to grab and create friction, and then it's going to cause that helmet to rotate right at that little impact. Again, they're extremely fast. We're talking 5 to 10 milliseconds. But that rapid turn of the head as it grabs something like the asphalt can really make a difference in how bad or how much risk you have for getting a concussion. So what we do here, we have this halo. So I put this helmet on this halo. We don't have a neck assembly, so it's just a free-falling head form with sensors inside. The helmet and the head form sit on this halo, and we can adjust this halo in any direction, whatever we want, X, Y, Z. We just adjust these prongs, and then, so that's the position. We use 6 locations and 2 energy levels to test our bike helmets. And the halo actually falls around the anvil. So as this helmet drops, the helmet hits the anvil, but the halo goes around it. So that's how we can keep the helmet in place as we do the helmet drop.
And that little thing to tighten it, the little knobby thing. Yeah, that's it.
Yeah.
Okay. Perfect. I'm gonna put it down here next to your arm.
Okay. I'm not going to go all the way up. We'll go up just enough to see you guys see what happens here. You ready, Mark?
Mm-hmm. Good.
All right. So 3, 2, 1. As you can see, that wasn't even very high. That was probably, I don't know, less than 5 feet off the ground. But, the impact to your head and that helmet's pretty significant. So, but that's how we test it. We have some fancy software that collects all that data, gives us resultant linear and rotational acceleration values. That gets plugged into our protocol or our equation. If you guys went onto our webpage and looked at any of the methodology papers, you'd see a fancy equation. Like for football, sum of 4 impacts at 3 locations, linear and rotational acceleration are included in there, and a risk function based on all those 2 million data points we have. So that's kind of how we do our bike helmet testing. Again, we're launching equestrian helmets, snow sport helmets, we're doing some sensors, we're getting rugby. In addition to those, we actually do some injury biomechanics research with some drones. And if Mark wants to cruise over here, we can show you these. So you guys have probably seen, there's recreational drones, but now there's even drones that are making deliveries, pharmaceutical drugs, and very lightweight packages. So you'll start to see these in commercial settings. And the FAA, along with some other regional organizations, want to make sure these things are safe, or as safe as they can be. And so we're actually evaluating them. So we crash these drones into the head forms to see what kind of accelerations occur. We also crash them into eyeballs and body parts and skin. How bad is that laceration going to be, etc. And so, how big they are, what they're made of, how fast they go, how many blades they have, how long the blades are, what type of material are the blades. This one's a hard plastic. So all those make a huge difference in the type of injury that they may cause. And so we evaluate those and try to inform the makers and the FAA, et cetera, what are the risk parameters. And so they're designing these drones to be a little bit safer. So that's one other part of our injury biomechanics research. We do a lot with the Hasbro company. Everyone's probably heard of Nerf darts and Nerf guns. So we'll show you these. So here we have a Nerf dart. And as you can see, as I push on that, it's pretty soft, right? So here's the knockoff version of the same Nerf dart, which is extremely hard. And so when Nerf designs these toys, and they know what kind of velocity the Nerf dart's going to come out of the toy, they know what kind of injury risk they're going to have, to kids that are playing with their toys. But when someone else makes these darts, these usually from Asia or some other country, they don't follow the same parameters, and so that's why the Nerf darts are probably a lot more expensive. They're a little more malleable, and these are hard plastic, and so they're cheaper, and you can buy a lot more of them. But they do cause or can cause serious injury. So we do a lot of research with the injury or with the toy companies to help keep kids safe. So anyway, so we got some equestrian helmets up here. Here's an old leather helmet. Again, so that's what they used before we went to plastic helmets back in the 60s, late 50s. This is a unique, people have probably heard of these airbag helmets or maybe airbag vests. Motorcycle riding, equestrian have safety vests with these airbags. But this one's called the hub ding. So a little knapsack goes around your neck. And then at a certain threshold of G's, that it'll ignite the nitrous oxide and inflate this helmet in really 1 millisecond. So it almost explodes as it inflates. This thing covers your whole neck and head. So it's pretty darn effective in protecting your head. Unfortunately, the Consumer Product Safety Committee, which evaluates bike helmets in the United States, has not approved this for sale in the United States because it's very unique. They don't know how to test it per se. We've done some preliminary testing. It's pretty darn effective. There's a couple research papers out there that kind of supports that notion. So you might see these a little bit more. Again, any helmet's better than no helmet, but the challenge with this one is, does it go off when you need it to go off, or did it go off when you didn't want it to go off? About $250, so not much more expensive than a regular helmet, but does have some pros and cons related to it. That's about all I have as far as a quick little tour. Zoom calls aren't always the most interesting since you can't see it live. So I appreciate you guys taking the time to tour the Virginia Tech Helmet Lab, at least virtually for now. If you're ever on campus, my email is on the website. Let me know. We'll get you in here so you can take a little look. Obviously, we'd love to have you. It's a great institution, very strong engineering programs, as you guys know. And so just anything you want to study is probably available in the engineering world here at Virginia Tech.
Thank you from everybody.
Thank you. All right. You guys are welcome. Yeah. If you have follow-up questions, feel free. I answer emails constantly. And so, but it's our pleasure. We like to share what we do. This is the Helmet Lab's part of our public service mission. We feel that we can inform the public on not only the importance of wearing a helmet, but the performance differences between helmets, because you as a consumer, you're shopping for a helmet. They're all on the shelf. They pass certification, but which one better protects me? And there's some big differences. Price doesn't always determine better protection. So we feel like we fill a big void and provide great customer service or consumer service, public service to those shopping for helmets. So again, thanks guys. Appreciate your time. Have a good night.